Fuel system part 7 or chapter slash module 7. Let's talk about fuel systems starting from the types and properties. Aircraft fuel systems are designed around the physical and chemical properties of the fuel they use. The two most common aviation fuels are aviation gasoline, avgas, and jet fuel, which is the jet A or kerosene. Okay. Avgas is used in piston engine aircraft and is characterized by high octane ratings to prevent detonation or like combustion before the time of the combustion phase. Detonation is when the fuel ignites before the combustion phase. We can call it a premature combustion. Common grades include 100 LL or low lead, okay, which is the lead within the fuel itself, which has a blue color for identification. Jet A is a kerosene-based fuel used in turbine jet engines. Okay, it has a higher flash point, higher ignition point, and a greater energy density than avgas, making it more suitable for high performance and high altitude operation. Okay, because you need a faster turn of the engines and at high altitudes. Okay, because there would be no hindering for the rotation of the engines at these altitudes. Meanwhile, for the turboprop, you would need something that combusts a little bit slowly, but has a higher torque. That's the difference. Okay, so if we want to compare, for example, between because imagine the avgas being diesel and the jet A being what do we call it? The fuel, the car fuel, okay? The benzene, okay? So what would be the difference between them? The avgas combusts a little bit more slowly, but it would combust longer, just like the diesel. The diesel combusts or it fires, it goes on fire for longer periods, okay? But it has a slow ignition. It has a slow incendiary effect, which would induce a higher torque for lower altitudes for the aircraft. Okay, higher torque for the turboprop, which is effective to move the engines. Again, here I'm comparing the avgas with the diesel fuel. Meanwhile, okay, if we compare the jet A with the benzene, so the characteristic of the same fuel that is used for motor vehicles such as cars, okay, it has a combustion which is a more explosive ignition. Okay, it can combust at lower temperature. Okay, and it's more like it goes on fire much faster than the diesel itself. However, the combustion itself burns quickly, so it is more suitable for lower torque requirement engines. Okay, for engines that have lower torque, okay, the benzene would be more effective. So this is why a six-wheeler usually runs on diesel, because it requires higher torque. It is a heavy vehicle, okay, a heavy transport vehicle, as you know. It requires a higher torque and a slow combustion rate. Meanwhile, your average car requires more the alternative. Okay, why? Because it needs to combust quickly, and it has a lower torque requirements, but more speed requirements. It needs the fuel to ignite quickly, much faster, in order to turn the engine at a higher rate. This is a display of the fuel system. You have the crossfeed when you want to transfer the fuel from left wing to right wing or vice versa. You have like fuel pump, the fueling valve, okay, you have the engine valve, left engine, right engine, okay, that opens up and close to increase the intake of the fuel within the engines, okay, and you have also here the APU, etc. Key fuel properties include density, or rho, viscosity, and volatility, how much volatile it is. A volatile substance or volatile fuel, specifically here, means that the fuel would evaporate so quickly if it's not kept within a sealed compartment, okay? And also calorific value, how much does it burn? How much does it generate heat? Fuel density varies with temperature according to rho equal m divided by v, where m is the mass in kilograms and v is the volume in meter cubed. As temperature increases, it becomes more volatile and the density decreases. Why? Because the molecules separate from each other. So you would have what used to be in the same volume expanding. So the mass would be lower per volume unit. Okay, that would be expressed as a lower density, which directly affects the mass flow and energy delivery within the engine. Fuel energy content. The energy released during combustion determines engine power output, of course. The heat of combustion for fuel, that is the factor that affects the generated power, is expressed by Q, which is the calorific energy or released energy, is equal to M, or fuel mass, multiplied by the energy, specific energy, okay? Lower heating value, which is the energy characteristic of the gas itself. Jet A generally has a higher specific energy per unit mass, okay, than avgas. So it burns much quickly and it produces much energy, but at a higher speed, at a higher rate. This is why it is more suitable for lower torque engines. Why? Because if it does that with engines requiring a higher torque, it will break the crankshaft, okay? That is what would happen. It would break like the engine handle. Why? Because for heavier vehicles, and again, going back to examples on the ground for the six-wheeler, like if you have a fuel that ignites very quickly, it would try to turn the handle of the motor very fast and it would break it. Why? Because it requires, again, a six-wheeler or a heavier carrier of whatever kind, heavier aircraft. We're not talking about jet aircraft, but an aircraft operating at a lower altitude, because the jet is something else. Okay, so it requires a fuel suitable for higher torque. Why? Because it needs to move like a heavier mass with a slow rate so that the handle of the engine won't break, just like a six-wheeler. Longer combustion, but a lower rate of the combustion itself, a lower energy delivery rate, okay, this lower heating value. Fuel tanks, pumps, and lines. Fuel tanks store fuel safely and supply it to the engine under all operating conditions. Tanks may be integral, so a part of the wet wing, okay, bladder type, or rigid tanks. Fuel is delivered from tanks through fuel lines using either gravity feed, so by dropping the fuel, that would be in the case when you have the wings are above the engine, or pumps to deliver the fuel to the engines, okay? Because in case they are at the same level, you need the pumps to drive the fuel needed for the motors. Pumps may be engine driven by the engine itself, or electrically powered booster pumps, standalone pumps. Fuel flow through a line is governed by, and this is called volumetric flow, by the way, volumetric flow rate is given by V equal A times V. E is the cross-sectional area of the pipe, okay? And V, lowercase v, is the fuel velocity or the speed of the fuel itself. Now, pressure losses due to friction and bends are critical considerations in fuel system design. Okay, why? Because they reduce the velocity of the flowing fuel, which would reduce the volumetric flow rate. So again, how we can visualize it? If you imagine this as being the pipe and this is the cross-sectional area. So A times V, which is the velocity of the flowing fuel, that product would give us the volumetric flow rate. Fuel quantity indication system or indicating system. Fuel quantity indicating systems provide the crew with information about the amount of usable fuel remaining. These systems may be mechanical, by the way, or electrical. Okay, mechanical sensors, which would be like a floater, okay, a floating part within the fuel tank, or electrical, that would be the sensor, okay, that would short the electricity when the fuel is detected. So you would mount multiple sensors at different heights, just like you would mount in the mechanical indication system, different floaters at different heights within the tank. So whenever a floater is like driven up, or whenever you have a short circuit at one of the indicators, at one of the electrical sensors, that would light up within the cockpit, that you would have fuel at that level, okay? Capacitive fuel quantity systems are widely used, okay? So the different level of fuel would change the capacity value of an electrical component, okay, in modern aircraft. The capacitance between the probes varies with fuel level, which is C equal epsilon A divided by D, where epsilon depends on the dielectric constant or permittivity of the fuel. Accurate fuel quantity indication is essential for flight planning, weight and balance calculations, and fuel management. Now here, to give you a picture, that would be the probe, okay, the electrical sensor. When it's dipped in the fuel, it would change the capacity, the capacitance, which is given by A divided by D times epsilon, where epsilon again is the dielectric constant of the fuel itself. Okay? Fuel metering and control. Fuel metering systems regulate the amount of fuel delivered to the engine to maintain the correct air-to-fuel ratio. In piston engines, carburetors, or fuel injection systems meter fuel based on the airflow and throttle position. Position of, like the position of the pedal of the fuel within the car, okay? The pedal of the oil inside the car, its position would determine how much fuel the engine is getting, as an example. However, in turbine engines, fuel control units, FCU, or full authority digital engine control, FADEC, systems precisely control fuel flow. Fuel mass flow rate is related to engine power. It's given by M, lowercase f, or denoted by MF, equal to power, engine power, divided by eta, multiplied by H, with eta is the engine efficiency, and H is the combustion rate of the fuel being used. Precise metering ensures efficient combustion and prevents engine damage. Another thing to be noted here is that when you have an excess of the fuel in respect of the air, okay, so when the ratio is more, like when the scale is more being pulled towards the quantity of the fuel against that of the air, or the volume of the air, that would result in an overcombustion or an overheated engine, okay? So there would be an excess of fuel being burned within the engine, which would lead at times to engine backfire. It means that the fuel is not being fully combusted, okay? Meanwhile, when you have a lesser quantity of fuel, that would lead to a lower exhaust gas temperature, okay, and a lesser efficient combustion. Fuel system failures and safety measures. Fuel systems are designed with multiple safety features to prevent fuel starvation, meaning the lack or the excess lack of fuel, leakage. So when the fuel is leaking out, it needs to be acknowledged or like detected by the system somehow, or fire hazards. Common fuel system failures are the following, but they include, but not limited, the following rather: fuel pump failure, the pump that propels the fuel all the way to the engines, it can fail, or fuel contamination, meaning a mixture between fuel and water that can lead to devastating consequences at times. Why? Because that can lead at times to fuel icing, okay, and an exceeding waxation due to the presence of water. Also, vapor locks, meaning that you could have vapor locked on the inside of the crossfeed that would lock or pressure, like it would keep the fuel from flowing from one part of the tank to another, from the left tank to the right tank, or vice versa. And fuel leaks, meaning when you have a puncture in the wing somewhere or in the reservoir in lower, like turboprop, smaller airplanes, okay? Because they house the fuel differently than the jet planes that house the fuel within the wings themselves. Vapor lock occurs when fuel vaporizes in the fuel lines, interrupting flow. Okay? The likelihood of vapor lock increases when the fuel pressure drops below vapor pressure. So the vapor would keep the fuel from flowing in such case, which is the premise P of the fuel is less than the pressure of the vapor. Safety measures include redundant pumps, which is, one of the most important feature is redundancy within the airplanes, okay, in order to have always a backup for a potential hazard or for a system that seems to be a weak point that can fail, okay, that is a liability, so to speak. You have fuel filters to get rid or to rid the airplane from the contaminants, fuel shut-off valves, okay, in order to shut off the fuel and prevent it from crossing from one tank to another in case you have a leakage in one of the tanks. Fire-resistant lines in order to resist or to counter any potential fire, and proper tank ventilation, okay, because the venting prevents from vapor locks. Fuel system components are designed to meet strict certification standards in order to ensure safe operation under all flight conditions, including icing, for example. Now, operational awareness. Effective fuel management requires understanding system design, fuel properties, and indication limitations. Continuous monitoring and proper procedures ensure reliable engine operation and flight safety.